Hey yo, can you help me lift the suitcase onto its wheels?
Just pull from the end of the suitcase instead.
Wait, what? Why is that so much easier?
Well, that's because of something called moments. The more you increase the distance from the pivot to the turning force, the less force you actually need to turn the object.
So what is the definition of a moment? Well, a moment is the magnitude of the force times the perpendicular distance from the pivot to the force. So let's say I had the scenario where I have this plank, and let's ignore the weight of this plank for the minute, and I have this force here acting of 50 newtons, acting 1 meter away from this plank, and a 10 kilogram mass acting 2 meters from the pivot. If I wanted to calculate the total moment acting on this body, I would have to say, well, the force due to this 10 kilogram mass is 10g before anything. And we can see that this 10g mass and this 50 newton force are both acting in the anti-clockwise direction. So the moment, as they're both acting in the same direction, because they're both looking to rotate the plank anti-clockwise, the moment is equal to this 50 newton force times 1 meter plus the 10g newtons force times 2 meters. So our total moment in this case is equal to 50 plus 20g Newton meters. That is the unit for moments. Let's say I now have this plank on its own and I've pivoted it here. Let's say that this plank is of 100 centimeters long and it's uniform. Now, what uniform means is that the mass is evenly distributed. And what you can therefore say is that the weight acts through the center of the object. So in this case, let's say I said that it was a 100 centimeter plank or a 1 meter plank. If I say that this length here is 30 centimeters, that means that this weight of this plank is acting in the 50 centimeter mark, which is right in the middle. And let's say it was of 10 kilograms, so it will be a 10g Newton force. And using simple maths, well, we know that this length is 50 centimeters. So this length here has to be 20. What force do I have to apply at this end in order to balance the moments? Now, at an equilibrium position, the resultant moment must be zero. So you can therefore say that the anti-clockwise moment is equal to the clockwise moment. In this scenario, the anti-clockwise moment is governed by this 10g Newton force. So the anti-clockwise moment is equal to 10g times, remember this is in centimeters, so we have to convert it to meters, so it'll be 10g newtons times 0.2 meters, which gives you a moment of 2g Newton meters. And this clockwise moment, well, is given by this force here, and that's at 0.3 meters away from the pivot. So we can say that the clockwise moment given by this force F is 0.3 F Newton meters. And based on this law of anti-clockwise moment equals clockwise moment, we can therefore say that when they're equal, 0.3 F is equal to 2g. So we can say that F is equal to 20g over 3 newtons. So in order to balance the moments in this case, I would need a force of 20 over 3 g. Now, one of the trickiest questions that will often come up in your papers, and not just in physics but in mechanics, in maths as well, is a ladder on a wall scenario. We are told that this ladder is at rest on this wall. And let's say it was a uniform ladder of 10 kilograms mass. So we can say that the force or the weight of this ladder is 10g. We are told that this wall is smooth, but we are told that the floor is rough. Now, what that means is that on the floor, we are going to have some frictional force, and in this case, it will be acting towards the wall. And also on the floor, we have the reaction force from the ladder. And on this wall, we also again have the reaction force which acts perpendicular to the surface, but because the wall is smooth, there is no frictional force. So I'll call this RF for reaction from the floor and RW for the reaction on the wall. And let's say that this was a ladder of 1 meter, so let's say this was 0.5 meters here and 0.5 meters there. And let's say it was an angle of 30 degrees to the horizontal. And the question asks, what is RW? Or in other words, what is the reaction force from the wall? Before we do that, we can quickly see that this frictional force has to be acting in the opposite direction of this reaction force from the wall, because we know that for an object to be at rest, the resultant force in all directions must be zero. So therefore, the forces acting towards the right must equal the forces acting towards the left. So therefore, this frictional force here is equal to the reaction force from the wall. And now for a body to be at rest or in equilibrium, two conditions must be met. Firstly, the resultant force must be zero. And we know that from Newton's first law. And secondly, the resultant moment must also be zero. What that basically means is that the clockwise moment must equal the anti-clockwise moment. These are two necessary conditions for a body to be at equilibrium or at rest. So let's go and find out how we can calculate this reaction force from the wall. The trick in this scenario is to identify where to take moments from. It is always important to state where you're taking moments from. We want to eliminate as many forces as we can. We want to only be able to work with the fewest number of forces as possible. So if you want to eliminate a lot of forces, it's best to take moments from the point at which those forces act. And here's why. Let's say I call this point A, where it touches the floor. If I take moments about point A, well, the moment from this resultant force and this frictional force is equal to, well, the resultant force times the distance, or the frictional force times the distance. And what you can see here is that the distance is zero, because it's acting at that point where you're taking moments from. So these forces don't play any role when calculating the moments about that point. So we can ignore them. So therefore, we're only left with this 10g force here, which is away, and this reaction force from the wall. So again, we do our normal thing of calculating the anti-clockwise moment and the clockwise moment. We know that moments is defined by the forces acting on the body times the perpendicular distance. So if we were to calculate the moments, say from the reaction force from the wall, we either need to find the perpendicular distance from the point to the force, or we have to resolve the force such that it is perpendicular to the distance. So there's two ways you can go about this. The first way is by extending this force out, and then you can just draw this line straight up and calculate this as your perpendicular distance. And we know that this length here is 1 meter in total, and if you're moving away from the angle, you use sine. So this distance here is equal to 1 sine 30, or just sine 30 meters. So the moment due to this reaction force, or the anti-clockwise moment, is equal to Rw sine 30, which is just a half Rw in Newton meters. The other way to do this is to resolve this force such that the force is perpendicular to the ladder. So we want to then work out what is this component of the force. Using normal trigonometry, we can see that this is an alternate angle. So this angle here is also 30 degrees. And therefore, you're moving this component away from the angle. So you're saying, well, this component here is therefore equal to Rw sine 30. And then Rw sine 30 multiplied by 1 is your moment, which is what we have here. It's the same thing. Your anti-clockwise moment in this case is therefore RW sine 30. And now you have to do the same thing for the clockwise moment. You have to resolve this 10g force such that it is perpendicular to the distance. So I can draw a line here, and we know that this angle here is also 30 degrees. So if I wanted to find this component of the force, well, I'm moving it through the angle this time. So this component is therefore 10g cos 30. So the total moment of the weight is a half times 10g cos 30, which is 10g times root 3 over 4. And therefore, by equating these two together, we can say that the reaction force from the wall is equal to 20g root 3 over 4, or 10g root 3 over 2 newtons. So it's always important to resolve the forces such that they are perpendicular to the distance that you're measuring, or calculate the perpendicular distance from the point where you're taking moments about to the force. And with this information, we have enough values to calculate the reaction force and the frictive force simply by equating the vertical forces equal to the upwards forces equal to the downward forces, and by equating the forces acting towards the right to forces acting towards the left. These latter questions are probably one of the trickiest questions that can come up in terms of moments in your paper. I advise you to go look at some practice questions in order to help reinforce what you've learned today. It's a good way to understand how to apply the content and the equations. Please make sure to subscribe, like and comment, and feel free to watch any of my other videos if that will help you with your physics course, and good luck for your future.